We're going to solve this problem using state diagrams. Normally, we think of states as the location of the ant, either on the bottom or on the top of our cube. But for this particular problem, we're going to represent a state as a movement that an ant takes. So for example, one possible movement that the ant can take is from one of the bottom vertices to one of the top vertices. So this movement represents one state. Another state is the movement of the ant from one top vertex to another. Another state is the ant going from the top to the bottom. The ant can also travel from one bottom vertex to another bottom vertex. Let's draw our state diagram. Here are the 4 possible movements that our ant can take, and we're going to fill in the probabilities. If the previous state that the ant was in was moving from the bottom to the top, the ant cannot go back to a bottom vertex because that would require going to a previous vertex, which the ant does not do. So once he's made that movement from bottom to top, the next movement that the ant makes must be from one top vertex to another top vertex. So this occurs with probability 1. When the ant has made a movement from one top vertex to another top vertex, the ant can now either go down to the bottom vertex or to another top vertex, but not the one that the ant was previously at. So there are 2 choices, equally likely, to either stay on top or return to a bottom vertex, each with probability 1/2. If the ant has traveled from a top vertex to a bottom vertex, then it cannot go back to the top vertex. So with probability 1, the next action that the ant takes is to move to another bottom vertex. If the previous action that an ant takes is to go from one bottom vertex to another bottom vertex, it can now go to a top vertex or to another bottom vertex, but not the one that it was previously at. Both of these happen with probability 1/2. We're going to use the state diagram to build out our probabilities at every step the ant takes. For some notation, this represents the probability that our ant moves, for example, from a bottom vertex to a top vertex on the nth move. This action only occurs if the previous action was for the ant to travel from a bottom vertex to another bottom vertex, and then with probability 1/2, it decides to go to a top vertex. And this is on the n-1 or the previous move. There are 2 ways that the ant on the nth move can go from one top vertex to another top vertex. If on the previous move, the ant had traveled from the bottom vertex to the top vertex, then this is always going to happen. But if on the previous move, the ant had moved from one top vertex to another top vertex, then the probability that he goes to another top vertex after that happens with probability 1/2. We have a similar probability on the nth move if our ant moves from the top to the bottom. This will only happen if on the previous move, the ant had moved from one top vertex to another top vertex. Also, if the previous move was from top to bottom, then our ant has to remain on a bottom vertex. Or if the previous move was from one bottom vertex to another bottom vertex, then with probability 1/2, the ant goes from one bottom vertex to another bottom vertex on the next move. The probability that our ant goes from the bottom vertex to the top is this expression, except at the start. And the probability that the ant goes from a bottom to a bottom is also not true at the start of the game, but we'll set our initial conditions to account for this difference. Let's start with the first step that our ant takes. Our ant starts at a bottom vertex with no history, so there are 2 ways that the ant can move to another bottom vertex and just 1 way that it can move to a top vertex. So the probability that it moves to a bottom vertex is 2/3, and the probability it moves to a top vertex is 1/3. Our ant is not starting at the top, so these probabilities are 0. To check our calculations, we can find the sum of these 4 probabilities, and if it's equal to 1, then we know we haven't made a mistake. We'll use our above formulas to fill in the rest of the table. For step 2, we'll find the probability going from top to bottom in the previous step and take half the probability from bottom to bottom in the previous step. The probability of going top to bottom is 1/2 of going top to top in the previous step, so that's still 0. The probability of going from top to top is the probability of going from bottom to top in the previous step, plus 1/2 of this previous probability. And the probability of going from bottom to top is 1/2 of the probability of going from bottom to bottom in the previous step. And checking, we see our probabilities add up to 1 again. I'll continue for n equals 3 and n equals 4. I'm going to pause here to notice that the probability we're on the bottom is 1/4 plus 1/4 or 1/2, and the probability that we're on top is also 1/2. We'll continue for the remaining 4 steps. Here are our remaining probabilities. The problem asks for the probability that our ant ends up at a top vertex after 8 moves. That's the probability that the ant goes from one top vertex to the other top vertex on the 8th move, plus the probability that our ant travels from a bottom to a top on the 8th move. So we find this sum at the end of our table and simplify. We're supposed to write this as m over n and give them the sum, which is 49. If there are any other AMC or AIME problems you'd like me to solve, please put them in the comments.